Hi all, I'm Arun Matthew. Today I'm here to talk with you about simple algorithm. Simple stands for semi-implicit method for pressure-linked equations. In the previous chapters, when we are solving, we assumed that the pressure field or pressure at nodes were somehow known. In the general case, the pressure with other flow variables emerges out of the overall solution. This is the general transport equation, and when we substitute u, v, and w in place of phi, we will get momentum equations in x, y, and z direction. These are the momentum equations in x and y direction, and this is the continuity equation. Here we can see that the pressure gradient term is written separately, and pressure gradient term is the main source term. When we try to solve these equations, we will face two problems. The first problem is the non-linearity of the quantities. We can see that the first term of the x momentum equation is the derivative of rho u square, and the first term of the y momentum equation is second term of the y momentum equation is the derivative of rho v square, which are the x derivative, which are derivatives of rho u square, which is not linear. And the second problem is these equations are intricately coupled, which means that the velocity component appears in all the equations and the continuity equation. You can see u appearing in all the equations and the continuity equation, v appearing in all the equations and continuity equation, and we don't have a separate governing equation for pressure, so we can't solve this equation. So these guys came up with an algorithm to solve this problem by adopting an iterative strategy. So you can see a flow field. This is the P node, this is the E node, and this is the velocity in the x direction. It will be stored in the E phase in a staggered control volume. We know that we can write AE as the summation of the neighboring grid points A and B, U and B plus source term. In the previous slide, we saw that the pressure gradient term was written separately from the source term. So here B will represent all the other any other body force other than the pressure gradient term. And when we integrate this pressure gradient term dou P by dou X with respect to our control volume, we will get PP minus PE. And when we integrate with respect to Y and Z, we will get delta X delta Y. Delta X delta Y is actually the area through which the flow in X direction takes place. See, we are considering the most general case, which is the 3D case. So the flow will be in X direction when we consider the X momentum equation, and there will be an area like this, right? Let me write. Yeah, there will be an area like this. So this will be delta Z and it will be delta Y. When we integrate the pressure gradient terms, when we integrate the pressure gradient terms with respect to x, y, and z. When we integrate with respect to x, we will get pp minus pe, and when we integrate with respect to y and z, we will get ae. So now we will divide the whole expression by ae. We will get an expression like this, which gives us the velocity field in the x direction. And capital AE divided by small ae will be written as dE, which is universally accepted, and it is given in taken in all textbooks. Similarly, we can write the y velocity and z velocity. So these equations can be solved if we know the value of pressure at nodes. Since we don't know the value of pressure and it is an iterative environment, we will actually guess the value of pressure. So P star will be the guessed value of pressure. So we will have PP star and PE star. Based on the guessed value of pressure, we will solve for the velocity fields in the x, y, and z direction. So this was our equation, and this is our equation based on the guessed value of pressure. When we use the guessed value of pressure, obviously the velocity field we get will not be correct. Therefore, we denote it by UE star. So AE UE star is the summation of A and B UNB star plus B plus AE into PP star minus PE star. When we subtract the second equation from the first equation, we will get AE into UE minus UE star equal to summation of A and B into UNB minus UNB star plus A. We'll get an expression like this. If we look at this, we can see that this was the correct velocity field in the x direction, and this is the incorrect velocity field we got when we guessed the value of pressure. So this is the correction needed to the velocity field. Here we can see that the correction at a point will be the combined effect of the velocity correction at a point will be a combined effect of velocity correction at neighboring points and pressure correction at neighboring points. Here UE dash is the velocity correction and PE dash is the pressure correction, as you can see. So we can see that the velocity correction at a point has an implicit dependence with the velocity correction at neighboring points. So we can't actually solve this equation. To make it solvable, we will actually omit this term. If we omit the velocity correction at neighboring points, the velocity correction at a point was dependent on the velocity correction at neighboring points and pressure correction at neighboring points. Now, when the velocity correction at neighboring points was omitted, the pressure correction will have to take the whole burden of correcting for velocity correction. So it will be like x is equal to y plus c, and if we omit the term y, z will have to become z plus y. So the second term, which is the pressure correction, will be overexpressed. So the velocity correction had an implicit dependence with the velocity correction at neighboring points. We have omitted the term. Velocity correction now depends on the pressure correction at the neighboring points, and the pressure correction at neighboring points will incur a velocity correction at the neighboring points. That's why this is known as semi-implicit method. there is no implicit connection between velocity correction at point and velocity correction at neighboring points, but there is a semi-implicit connection. These semi-implicit have nothing to do with the time-dependent semi-implicit methods like Crank-Nicolson we have studied earlier. Now, after we omitted the second term, we will get an expression like this, which says AEUE, which means velocity correction at a point is the effect of pressure correction at the neighboring points. Here, when we divide the whole expression by AE, we will get velocity correction equal to dE into PP dash minus PE dash, where dE is equal to AE by small ae, which I was said earlier. So the velocity at in the z direction will be the guessed value plus the correction needed. The guessed value here was UE star, and the correction needed we have found it to be UE dash. We substitute the value of UE dash, and we will get an expression like UE star plus dE into PP dash minus PE dash. Since this is an iterative environment, the new velocity field will be the next velocity field. This is the velocity field at E now. Similarly, we can write for y direction and z direction. Now, to implement this formula, we have another problem, which is we don't have the value of pressure correction. We will be trying to get it. So, to get the pressure correction, when we solve these equations, we need a velocity field which must satisfy the continuity equation. So when we get a velocity field which satisfies the continuity equation, we will get a pressure field which confers to a continuity equation satisfying velocity field. So the continuity equation acts like a governing equation for pressure correction. Hope you understood that. So we write the, please note this velocity correction at in x, y, and z direction. The continuity equation is written as dou p by dou t, dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equal to 0. Now we will be integrating the expression with respect to main or collocated control volume. This because we are integrating it to get pressure value. If we want to get the value of anything other than velocity, we will be integrating with main control volume. And if we want to get velocity, we will be integrating with staggered control volume. So when we integrate the first term with respect to time from t to delta t, and with respect to x from w west to east, with respect to dy from south to north, with respect to dz from bottom to top. Similarly for second term, with respect to x from w west to east, with respect to dy from south to north, with respect to dz from bottom to top, and with respect to time from t to delta t. T to delta t. Thus, third and fourth term can be expressed in similar way. Now, when we integrate the first term with respect to time, dx, dy, and dz, we will get an expression like this, which is rho p minus rho p old into delta x, delta y, delta c. And the second term will be like this, where which will be rho u at east minus rho u at west into delta y, delta c, delta t. When we divide the whole, similarly for third and fourth term, we can write like this. When we divide the whole expression by delta t, we will get rho p minus rho p old into delta x, delta y, delta c divided by t plus these expressions, which will be equal to 0. Now we have noted this velocity field in the x, y, and z direction. So in the expression we got, we will be substituting the value of ue, v, n, and wt. Taking this term, we will be substituting the value of ue as ue star plus de into pp dash minus pe dash, and uw, as you can think, it will be uw star plus dw into pw dash minus p dash, which is shown here. We can write in the y and z direction, but it will be similar to this, so I am not writing it. When we express the whole equation like this, and substituting the value of ue, vn, and wt, we will get an expression which will be similar to AP PP dash equal to AE PE dash plus AW PW dash plus AN PN dash plus AS PS dash plus AT PT dash and AB PP dash plus B, where AE can be found out to be AE will be the coefficient of PE dash. So it will be DE will be there, rho E will be there, and delta Y, delta C will be there. It will be negative value. So when we take it to the right side, it will be positive, which is written here. Rho E will be there, DE will be there, and delta Y, delta C is there. Delta Y, delta C is there. Similarly, for W, we can write rho W, DW, delta Y, delta C. Similarly, AN, AS, AT, and AB can be found out. Now, what's B? B is the remaining terms. From here, we can see this will be included in B. So when it will be taken to the right side, it will be rho P naught, rho P old minus rho P into delta X, delta Y, delta C divided by T, which is written here. Rho P naught minus rho P, delta X, delta Y, delta C. Now there will be the star terms. These are the star terms. There will be rho E UE star into delta Y, delta C, rho E UE star, delta Y, delta C. It will be positive in the left side. So when it goes to the right side, it will be negative. That's why it's written as minus rho E UV star delta Y delta C. Similarly, there will be rho W UW star delta Y delta C, which will be negative in the right side, and when it goes to the when it will be negative in the left side, when it goes to the right side, it will be positive. So we will get an expression like this. By taking a close look at this equation, we can see that this shows the net flow rate in minus out in the x direction, and this shows the net flow rate in minus out in the y direction, and this shows the net flow rate in minus out in the z direction. And we can see that this is when we look at a close look, we can see that this is the rate of change of mass inside the control volume. So actually B, this expression, which is B, is a measure of satisfaction of conservation of mass, which means if B equal to 0, mass is conserved. Similarly, if B equal to 0, there will be no pressure correction and P dash will be 0. This is a measure of satisfaction of conservation of mass because it was derived from continuity equation. So we can use this to solve for P. This expression we have written this expression. This is known as the pressure correction equation. These are the values of all the E, A, W, A, N, etc. terms, and this is the value of P. So the value of pressure will be equal to the guessed value of pressure plus the correction needed. Now we can iterate this till convergence of conservation of mass. So to summarize, in the first step, we guess the value of pressure. We guess the value of pressure. With the guessed value of pressure, we solved for momentum equations, which gave us velocity field in the x, y, and z direction, which was incorrect. Which will be u star, v star, and w star. With that, we solved the pressure correction equation. This equation is the pressure correction equation. Using the step 3, which is solving the pressure correction equation, we updated the value of velocity. With the in the step 5, we corrected the pressure value to be guessed value plus the correction needed. Now this P will be our new P, which will be used in step 1, and we will be iterating this till convergence. These are the derivatives from simple algorithm, which is modified version of simple algorithm, and you can read about this in this book. These are the references I took to make this presentation. Hope you all understood something about simple algorithm. You can read more about this, and you can watch the NPTEL lectures to understand more. And thank you.